All right. Um, okay, so um, the only reason that we use recursion is that there are oftentimes, particularly when we have a really complex algorithm that we're trying to use, where it becomes doable to write it using recursion, whereas writing it using iteration would just be like a huge challenge. So some algorithms become much easier to write when we use recursion, and usually it's the case that recursion actually turns out to be less efficient than the exact same algorithm if it's implemented using iteration. So sometimes what people will do is they'll write the algorithm using recursion and then they'll translate that recursion into iteration. Anyway, main point there, I just wanted you to know that we're not gaining any new power here in terms of what we can accomplish anyway. Third, and this is a big one, there are always two different ways of looking at a recursive solution to a problem. And 95% of students make the error of naturally migrating towards one instead of the other. And that is the best way to look at recursion when you're just trying to design your algorithm is something I call the leap of faith method. As you'll soon see, when we write a recursive function, we can assume that the function we are writing already exists and works as desired. So there's some caveats with that, and we'll get into that a little bit more. But that turns out to be hard for students to really believe till you get used to it. So the sooner you can get yourself to use that fact and trust it, the better you'll be at writing recursive functions. The other way of looking at a recursive solution is to try to follow through, trace through step by step every single little detail of what's happening inside the computer when the recursion is being executed. I guarantee you that I will get several questions during this lecture, and maybe not this time, but normally when I'm not in such a rush, where a student will say, yeah, but what about when this happens and this happens and this happens? And I'll say, you know what, we can go there if you want, but for now, the best thing to do is to leave those details aside for now and just look at this from a higher level. And we're going to talk a lot about how to do that. Fourth thing I want to say is that there's sort of a technique for writing a recursive function. Sometimes it's harder than it is with iteration to see where things are going when you first start. So you may have to just sit down and start going through the steps. And as you start going through the steps, you may, in the end, realize how it's going to work. You may not have that whole thing figured out right from the start. Excuse me for a second. I got to take a quick timeout here. All right. So what we're going to do to learn recursion is we are going to do an example. We're going to write a function that I'm going to call power, and it's going to take two parameters, a base and an exponent, and it's going to return the result of taking that base raised to that exponent. So let me get a file going here. Okay, so hopefully you're all seeing a blank um, file at this point.
Yep, we can see it.
Good. Okay, so our function is going to look something like this. All right, guys, I'm going to have to take another like 30-second pause here because I got to move. Give me a second. All right, you guys still seeing the code?
Yep, we can see it.
Yes, sir.
I just realized I should have turned the recording off while that was happening. Oh well. Um, okay, so when you're writing a recursive function, the first thing that you're going to ask yourself is, what is the base case? So the base case is used to make sure that the recursive function does not keep going indefinitely. Of course, if the function calls itself every time it's called, then it's never going to stop. So there's got to be a situation in which the function does not call itself. So when we're thinking of the base case, what we're looking for is we're trying to think of a situation that where this function can return the result immediately without having to do any sort of calculation where it has to call the function again. In addition, it should also be the simplest possible such case. So in our power function, give me a second to go back. You know what, guys? I'm really sorry about this, but this is not working. I'm going to have to move it. All right. I think this is going to work this time. um, everyone's still with me? Okay. Um, so I'm just going to take an aside for a minute. Let me, is there any way to just pause the recording? Pause recording. Good.
There are the feedback buttons like yes and no and raise hand, which you can see in the participants tab pretty easily.
Yeah. I may end up using those at some point, but it always just seems like it's going to take such a long time to me. But yeah, I'll probably end up trying that. Okay, so let's keep going. So basically what we need to do now is figure out what we're going to do in the recursive case. We've got our base case taken care of. Figure out what to do in the recursive case, we're going to be done. So there are, even if we have absolutely no idea how this is going to look at this point, there are several things that we can do that are kind of hints to get us going in the right direction. But let me just give you the overall picture first. Basically, what we need to do here is we need to figure out some way to figure out what the answer is, keeping in mind that we already have a function named power that we can call to do the work. The caveat there is just one hitch, and that is that when we call the function, the power function, we have to call it with arguments that get it closer to the base case. Does that make sense? So, you know, we couldn't just say
increment or decrement.
Right? That would follow my rule about assuming that there's a function named power that we can just call. The problem with that is that it doesn't get us closer to the base case. So
Infinite loop.
Right, exactly. We'd have an infinite loop there. So
You just got to decrement, right?
Right. So if we think about, okay, what are we going to do to get us closer to the base case? Well, if we call the power function with exponent minus 1, that's going to get us closer to the base case. Does that help us? Can we use the result of base raised to the exponent 1 power to get our final answer? What do you guys think? Anybody have any ideas about that?
Could you repeat the question?
How could we use, so first of all, this isn't going to be quite right? This is going to be wrong because it's going to, if I'm taking 2 to the 5th power, this is saying return 2 to the 4th power, which isn't correct. What do we have to do to this expression to make it so that I'm actually returning the right thing?
Change base to base equals times base, or times equals base.
I'm sorry, say that again.
Change that base to base times equals base.
And that's, you know, that's going to give us, like, if the original, if base is 2 and exponent is 5.
Oh, you're right. Yeah, that
this would
won't
be
work.
saying 4 to the 4. So that's not quite right. But, you know, think about it. Think about it this way. This is what we want the function call to be. And if you think about algebra, if I tell you, I don't know what 2 to the 6th is, but I know what 2 to the 5th is, can you figure out how would you figure out what 2 to the 6th is?
2. Or 2 times 2.
Multiply by 2, right? Everyone follow me on that? If I say, I'm not telling you what 2 to the 11th is, but I'm telling you that 2 to the 10th is 1024, what are you going to do to tell me what 2 to the 11th is?
Basically
multiply the judge by base.
Multiply by 2, right? So I just sort of did some reasoning and I decided, okay, if I know what power of base to the exponent minus 1 is, I can just multiply that by the base, and that will give me the correct answer.
Oh.
Take a look, stare at that for a second. Tell me if you think that makes sense. Yeah.
Why exponent minus 1? I just have a question on that. Why
Okay,
exponent
so
minus
there's
1?
a couple of ways to answer that. The first reason is that we know when we call the function recursively, we have to give it an argument that's getting us closer to the base case, right? And the base case is exponent equals 0. So I know if I subtract 1 from the exponent, that's going to get me closer to the base case. That still begs the question, well, why not exponent minus 3 or exponent minus 7 or exponent divided by 2 or something like that, right? So you do have to use a little bit of judgment to decide, okay, what's going to be really helpful here is if I know what the power of base to the exponent minus 1 is, I can actually use that information to figure out the final answer. How did I do, Robin? Did that help at all?
Not I thought it was because you know, in memory you come from 0, 0, 1, 3 instead of 1, 2, 3.
That isn't related.
Oh, well, then I'm lost.
So I mean, so I know that I have to put an expression in here that is going to call the power function with something that's closer to the base case. Does it make sense that exponent minus 1 gets me closer to the base case?
Yeah.
Okay, so the reason I used exponent minus 1 instead of some other way of getting closer to the base case, you know, that involves some just sort of problem solving, thinking it out. You know, whether it's exponent minus 1 or exponent minus 7 or exponent divided by 2 or whatever, all of those would get me closer to the base case, right? So that the important thing at this point, I would say, is just understanding that what goes there has to get me closer to the base case. And then each problem you do, I think, you know, this part just kind of takes some practice, figuring out whether it should be exponent minus 1 or some other way of getting closer to the base case. Thinking about it more mathematically, you know, in math, we know that x raised to the n power is equal to x times x raised to the n minus 1 power.
Ah, okay. Now I got it.
So that's kind of what we're doing here. Every recursive problem isn't going to work itself out nicely into an algebraic expression like this, but that's basically the idea.
Okay. Okay, thank you.
All right. All right. Any other questions about this recursive function? I could put it in a program and run it to prove to you that it actually works, but I think I will ask you to take my word for it. Okay. The next couple of things I would normally do is I would go through a couple of processes where I actually trace through this code in excruciating detail so that we can really see what's going on behind the scenes that makes this work. I think I'm going to skip that at least for now, and maybe at a later date, if someone really wants me to go over that, I can, or you could go look at the video online. But for the most part, I'm trying to get you to avoid that process if you can. The only reason we even need to have a process like that is in case we do our best to write a recursive function staying at the top level like this, and then it turns out that we have a bug in there and we've got to figure out what's going on. In that case, we may have to just sit down and go through the step-by-step in excruciating detail. but I'm going to at least postpone, if not skip that discussion, unless there's an outcry. I think what I would like to do is go on to another example. What I really need here is 2 screens. I don't know why I haven't thought of that before. All right, let's write a function named find smallest. And its parameters are going to be so an array of integers is how many items are in the list. Okay. The job of this function is to return the smallest item in the array. So, well, first question is, what's the base case going to be? Anyone who, there's still a few of you who haven't said a word, so if any of you haven't said a word, I have an idea of what I think. And by the way, I love it when I get wrong responses because it gives us something to talk about, right? If you say a wrong response, it probably means that's what everyone else is thinking too anyway.
So would the base case for this one be when there is only one thing left?
Right, if there's only one item in the array, I would say that slightly differently, right? I would just say there's only one item in the array, then that item is clearly the smallest item, right? How do we know if there's only one item in the array?
If num items equals 1.
Right. So, okay, so if num items is equal to 1, what are we going to do?
Return list num items, or return.
So if there's only one item in the array, where is it?
The
Zero.
list sub
0, right?
Yeah, 0.
Okay. There's our base case. All right, so if we have more than one item, well, let's talk about, let's state what we're going to return now. So we know this is a value returning function, right? So we know that our else statement is going to return something, right? We know this is a recursive function. So somewhere in this return expression, we're going to have the smallest function. What do you suppose the arguments are? So what I'm doing right now is I don't know exactly what's going to go here yet, but I'm kind of filling in the pieces that I can. I know it's going to return something. I know that the return expression is going to have a function call to find smallest of it. Do I know what the arguments are going to be? What's the first argument going to be?
the list still.
The list, yeah.
Okay. And then what do you suppose the second argument is going to be?
The num items, number of items.
-1.
Okay, so first, let's look at this. I want to make sure everyone can see why that's not going to work. Why is that not going to work?
It's not reaching the base case.
Not getting me closer to the base case, right? So let me just take a guess here. -1 is a pretty good guess, right? Okay. So I'm just throwing that out there so we can look at it and play around with it. What is this function call going to give us? If we say it very precisely, you know, just an English, a very precise English sentence telling me what that's going to give me.
The smallest item in the list -1 of size -1.
Last element.
Okay. So that was correct. I might say it like this. It's going to give me the smallest item in the entire list, not counting the last item, right? Going to ignore the last item. So it's going to give me the smallest item in the entire list, not counting the last item. Everyone with me on that? And so, and we can just call the function to do that because it's a recursive call. So if we know the smallest number in the entire list, not counting the last number, how can we use that information to figure out what the actual smallest item is? Just English.
Keep going until there's only one item.
Well, okay, so you're doing the thing where you try to see how this is going to end. Okay, I want to keep it at the top level here.
Right now, we're not actually ever comparing any items.
Not yet. That's true. But let me tell you this. Okay, let me ask you this. If I tell you here's a list of 1,000 items, and I will tell you that the smallest item out of the first 999 is 7. How can you tell me what the smallest item in the array is?
You would have to compare that to the last one that you're taking off the end.
Right. So compare that the smallest item out of the first 999 with the last item, and return whichever of those two is smallest. Right. That makes sense. So I'm going to say else if okay, so this is basically setting up what I just said, right? If the last item in the array is less than the smallest item out of all the other items in the array, then what am I going to do? By the way, I'm very comfortable with silence. I don't feel like you have to jump in just because no one else is.
You're going to have to
Return list and num items -1.
Right. Everyone clear on that? So, and then if that's not the case, then, let's see. Let me try this, okay? Someone raise their hand, and I will call on someone to tell me what's going to go here. When I see that someone's raised their hand, it's louder than on mine. You guys know how to raise hands? It's in the participants menu, right?
Yeah, there's 2 people already raising hands there.
Oh, okay. I see. Okay, Kaylin, go ahead.
So if the last item's not, if it's the smallest, then we're gonna return that. But otherwise, we want to return the smallest in the rest of the list. So we can just return find smallest list num items -1.
Okay. Before we go any further, just let me say we're going to work on this code a little bit, but leaving it the way it is right now for now. Anybody want to ask a question about what's going on there? Everyone clear on what's happening? Let me just go through it in English real quick. So we're saying if the last item is less than the smallest item out of the rest of the list, then return the last item in the list. Else, return the smallest item out of all the other items in the list. Does that make sense? Anyone want me to do that again?
Can you do that again? I couldn't hear.
Sure, I will try it. I will do it one more time. So here we're saying if the last item in the list is less than the smallest item out of all of the other items in the list, then return that last item in the list. It's the smallest item. Otherwise, return the smallest item out of all of the other items in the list, not counting the last item. So
Okay.
the key thing here is that we have this function called find smallest that we can call, and we know that it will correctly return the smallest item in its argument as long as it's getting closer to the base case. Okay? Questions? All right. There is some ugliness to this. In a recursive function, making recursive calls multiple times is extremely inefficient because each time you make a recursive call, that could result in a whole bunch of additional recursive function calls, and the number of function calls grows exponentially. So we're going to try to, and you know, even if it wasn't recursive, we might want to do this anyway, but we're going to try to improve this a little bit. Let's first assign a local variable to that result, and then we can just use that variable in here instead of the function call. Oops. Save this. Okay, any questions about what I just did? Didn't really have anything to do with recursion, just cleaning my code up a little bit. Let's actually go ahead and run it this time. Oops. Yeah. How's that look? I just put a bunch of numbers in the array and then call find smallest. Hopefully they
Looks like
return.
it might run.
Looks like it might run. Close enough to give it a try. If I click new share, I click here, did that just switch what I'm sharing, or are you looking at
It
TV?
works perfectly.
Yeah.
Oh, so, but now you can't see the code, right?
Yeah, that's correct.
Okay. So not ideal, I guess. Let's try it out. Oops, hold on. Smallest item in the list is 1. So I know I should probably just try my desktop. That's what we were hoping for, right? Okay, I can't resist. I'm just going to take 1 minute. I'm going to make this even better. Basically, what we're saying here in this code right here is return whichever is smallest between the last item and the smallest item out of all the rest of the list, right? So I'm going to replace all of that code with just does that look?
Personally, I would make num items minus 1 equal to end and then use end instead, but that's just me.
What instead?
I would declare num items, or sorry, define end to be equal to num items minus 1 and then just use end in both places. But that's a personal thing. It's not necessary.
I bet I would certainly prefer to have the more descriptive variable name, but anyway. Let's just check this and make sure. Well, and actually, it turns out I'm missing a closed parenthesis. Anyway, okay. Any other questions about that example? All right. I think what I'm going to do is I'm going to skip the next example. You can read about it in the lesson, or you can watch it in the video. I'm going to skip ahead to our last example, which is the Towers of Hanoi example. So the story behind this is, I'm going to just read this to you real quickly, just because it makes it a little more fun, I guess. So there's a story. There's a story or a tradition in the mountains near the city of Hanoi. There's a Buddhist monastery. Outside the monastery, there are 3 tall towers, which we will call left, middle, and right. And there are 64 stone discs. Each of the discs has a hole in its center so that it can be placed on one of the towers. So you're going to think of the towers as poles that you stick discs on. Each disc is a different size. At the beginning of time, all 64 discs were stacked on the left tower, ordered from largest on the bottom to smallest at the top. Day and night, the monks who live in the monastery unceasingly moved discs one at a time from one tower to another. They never place a disc on a tower that holds a smaller disc. And when they have moved all 64 discs from the left tower to the right tower, it will be the end of time. So what we're going to do is we're going to do a little investigation. We're going to write a recursive function to simulate the towers of Hanoi. And then we're going to do a little analysis to see how much time we think we may have left. So I think what I'm going to do is I'm going to just share my I just realized I was completely ignoring the chat. Usually it beeps at me or something when there's a chat. But anyway, I'm going to share my desktop. I can get that. Okay, so can you see my little Towers of Hanoi simulation here?
Yes.
Okay, so this is just to give us an idea of what we're working with. You know, to solve this problem, we could move, say, one disk to the right tower, one disk to the middle tower, one disk back to the middle tower, and move the big disk to the target tower. Move that one out of the way. Middle disk to the target tower, small disk to the target tower, and we're done. Let me do it again with 4. And I'm gonna, we're gonna make a couple of observations as we go this time, okay? I happen to know that if it's an even number of disks, then you want to move the first disk to the temporary tower. If it's an odd number of disks, you want to move the first disk to the right tower. But that's actually not going to have anything to do with our solution. So here we go. I'm going to move the small disk to the middle tower, which I'm calling the temporary storage tower. Move second disk to the right. Move small disk to the right. Move third disk to the storage tower. Small disk back to the source tower. Second disk to the storage tower. Small disk to the storage tower. Okay, so let me ask you this. Roughly speaking, what percent of the way are we through solving the problem
Since we can see the minimum number of moves, about half.
now? Okay. Yeah, that's the one disadvantage to this. Pretending that you can't see that, is there any way that we could think about what percentage of the way we are through the problem now?
The amount of steps it took us to move 3 rings last time.
Okay, but what does that have to do with
When you-
maybe?
Well, because when you only had 3 disks, it took you X number of moves to get them from one pole to another.
Okay,
You're going to have to do that again, that number of times again, once you move the 4th largest disk to the final pole.
got it. Right. So the way I would say that, and not only am I going to repeat the question, I'm going to give the answer, is that we have now gone through about half of the process, right? Because we could think of the process as moving all but one of the disks to the storage tower, then moving the bottom disk to the target tower, and now what's left is we just have to move all but one of the disks to the target tower. That make sense? So how many more moves do we have? Without looking at the minimum moves. It took us 7 moves to get 3 disks from the source tower to the temporary tower. So now it's going to take us another 7 moves to get those 3 disks from the temporary tower to the target tower, right? 1, 2, 3, 4, 5, 6, 7. Okay, so does anybody? I'm kind of curious. For how many of you did anything that I was talking about in there sort of remind you of recursion a little bit? Anybody? Not really. Okay, 1. Yeah, that would be a good time to raise your hand. So, right, when I say moving all of the disks except 1, that sounds a little bit to me like a recursive call, subtracting 1 from one of the arguments, right? Okay. So here's what we're going to do. We're going to write the code for this. We're not going to write code that actually draws pictures and stuff. We're just going to write code that that gives us a list of instructions that tell us the steps involved. Sorry, let me give it to you. So, and basically what we're going to count on in our solution is we're going to say, move all of the disks except 1 from the source tower to the target tower. Then from the source tower to the storage tower. Then move 1 disk from the start tower to the target tower. Then move all of the disks except 1 from the storage tower to the target tower, and then we're done. The 3 steps. All right, let's I wonder if I'm ever going to get good at using Zoom. Okay, so I'm going to have, now you guys are just looking at my code, right?
Yes.
I'm going to say constant. And then I'm going to do this here. My main function is just going to be a call to the move disks function. I'm going to say move disk. And we're going to give names for the 3 towers. I'm going to call them left. Okay? We could call them whatever we want, right? We could call them pole 1, pole 2, pole 3, tower 1, tower 2, tower 3. I'm going to call them left, right, and middle. So then I'm going to have a disks function. So it's taking the number of disks. The second argument is going to be the tower that we are using as the source tower. Next argument is going to be the tower that we are using as the target tower. And finally, the storage tower. Okay, so the job of this function is to print out the steps that we will need to take to move this many disks from the source tower to the target tower. So I'm ready to start writing this function. Maybe I will just get my prototype set up here. Anybody want to ask a question or have me talk a little bit more about anything before we dive in? Okay. So, base case. Someone raise their hand and tell me what the base case is going to be. Or take a guess. So if I want to see raised hands, I look in the participants window, which only shows me like 5 out of 10. Maybe I can make it higher. All right, I need to hold on for a minute and see if. Okay, Mark Guerrero, you want to take a shot at it?
Base case is going to be when there's no moves left to make.
No
So
moves
when,
left to make.
Num disks is equal to 0.
Right, right. If
So
num
when num
disks
disks is equal to, I guess not that.
No, I think you're right. I think.
Sorry, you're cutting out.
I'm cutting out?
I can hear fine.
Okay.
I'm hearing too.
I have god awful internet, not you, 100% me.
Okay. Anyway, the first thing I heard was num disk is 0, and that's absolutely correct, right? The time when we know that we are done is if num disks is equal to 0, we don't make any moves, right? And we're done. So if num disks equals 0, what do? We do
Return
nothing.
0?
Well, this is a void function.
Oh, I did.
So basically, if num disks is 0, we're going to do nothing, right? And then we're going to say else, and we're going to have a base case. However, this is kind of an awkward way to say it, right? This is equivalent to just saying if num disks is greater than 0, then do whatever's in the else part. Everyone with me on that? So instead of this, the only reason I did it this way is that's sort of the usual format of a recursive function is you say if base case, else recursive case. In this case, that doesn't really work out too well. So, and you'll see this. So we're going to just say if num disks is greater than 0. And in here, we are going to do our recursive case. Okay, so this may throw you when you start writing recursion on your own. So I just want to emphasize, we still have a base case and a recursive case here, right? It's just that the base case is implicit. You can't actually see it, but it's still there. The base case is when numDisks gets to 0. Everyone okay with that? All right. Okay, so we have figured out that numDisks is not 0. So we're going to have to go through our 3 steps. I said the first step was move all the disks except 1 to the storage pole. Second step is move 1 disk from the source pole to the target pole. And then the third step is move all the disks except 1 from the storage pole to the target pole. So source to storage using the target pole as a storage pole. That make sense? Probably the most confusing thing about this example is that the roles of the poles keep changing, right? Well, so we're taking the source. We want to move from the source pole. We want to move disks from the source pole to the target pole. But to do that, we're first going to move disks from the source pole to the storage pole, and we're going to use the target pole as the storage pole. Does that make sense? Can I say that again?
Could we get that one more time, please?
Yeah. So our goal here is to move disks from the source pole to the target pole. In order to do that, the first step is going to be to move disks from the source pole to the storage pole, using the target pole as the storage pole. And in the interest of time, I might not do this now, but if we went back to the little game I was playing, you'd see the first thing we did was we moved all of the disks except 1 over to the target. We moved all the disks except 1 over to the storage pole. And the way we did that is we used the target pole, the right pole, as sort of a temporary storage place, right? So the thing that's happening here with the recursion is that we keep switching the roles of the different towers around. How clear are we on why this is the correct first step? Does that make sense?
Yeah.
Anybody
I have
want
a
to ask
question.
Yeah, go for it.
You mentioned before when you were showing us the game that if it's an even number of disks, then you will use the most right tower, right? And if it's an uneven, then you will use the storage pole first.
I think you might have that backwards, but
Okay. Well, either way, my point that
Right.
I was trying to ask about is, do we write that in code to give instructions, like where to put the first piece, or?
that actually, as it turns out, that actually is not going to come into our code. It's actually going to work out that way when the problem is solved.
Okay.
But because what we're doing here, the first thing we're doing is not figuring out where to make the first move, right? The first thing we're doing is figuring. So yeah, the algorithm will figure that out.
Okay.
All right, so moving. So let's just go. Let's say numDisks is 4. So the first step is to move 3 disks from the source tower to the storage tower. The second step is just going to be to move 1 disk from the storage tower to the target tower. Sorry, I'm having a little trouble with my screen space here. Source, tower. Okay, so that's the second step. Third step is going to be now we move those num disks minus 1 disks that we moved to the storage tower, move those from the storage tower to the target tower using the source tower as the temporary storage location. So move disks, one of them, from the storage tower to the target tower using the source tower as the storage tower. Okay. Go ahead and stare at that a little bit. You may need to go back and read through the notes a few times or whatever before this actually makes complete sense. But let's go ahead and give it a try. Okay, so here's the result. And we probably don't want to take the time to go through every step, but it kind of looks like we can go through it enough times to see that it looks like it's doing the right thing. Left tower to middle tower, left tower to right tower, middle tower to right tower. So far we moved 2 disks to the right tower. Left tower to middle tower, then right tower to left, right tower to middle, left tower to middle. Now we have 3 disks at the middle tower, right? Then move the left tower to the right tower. That's the bottom disk, moving it from the left tower to the right tower. And then these 7 moves are going to move those 3 disks from the middle tower to the right tower. Okay? All right. Next question. How long is it going to take to move 64 disks? Here's what I'm going to do. I'm going to comment out that cout statement.
At the runtime.
Yeah, because that's what's taking up 99.99% of our processing time. Okay. I'm going to change num disks to say 15. And if I had time, I would actually put a timer in here, but let's just, maybe someone can time it or we can count seconds or something. Let's just see what happens if I run this now. Oh, here's what I need to do. Cout. Start. Oh, that was pretty fast, right? So I try 20. Let me try 19. Still really fast. Okay, my computer's too fast. Let me try 21. Did you see a pause? I think we at least got a pause that time.
Exponential, so we'll get there.
Right. Okay, a little more of a pause. I should have started a little higher than I did, but we're getting there. 23 disks. Watch carefully. No, that was like maybe 2 seconds. Let's call it 2 seconds. Let me ask you this. if it takes 2 seconds to move 23 disks, how long is it going to take to move 24 disks?
Longer than we have time to wait for.
Yeah. Remember, if I moving 24 disks means move 23, then move 1, then move 23, right? So roughly speaking, we're basically just doubling every time we increase in by 1.
Exponential.
Yeah, so it's exponential. So if it took 2 seconds to move 23, how long is it going to take to move 24? About 4 seconds, right? Because we're doubling. Let's test that out. Oh, I didn't change it. Yeah, that was about 4 seconds. I probably counted too fast, but, and so then if I change it to 25, it should be about 8 seconds, right? Yeah, maybe not quite, but you get the idea. So we're sort of out of time, and my battery is at 1%. So I'm probably going to keep talking in a second. But you can figure out that the number of moves. Yeah, maybe I'll just talk about that a little bit next time. It doesn't have anything to do with getting your assignment done. It's just kind of fun stuff. So I think I'll start off our next class just kind of wrapping this up for fun, or you can watch it in the lecture video. All right, I'm going to call it a day, and I'm going to end our.
Almost got it.
I was curious how many moves it takes,
I
though.
think his
Like,
computer died at the last second.
Yeah.
Sure, I know.
1% doesn't last very
If you're
long.
curious, you could always just copy and paste. Especially when you're actually using your computer heavily. The Zoom and actually running programs.
Yeah, right. Throw it off a little bit.
So did anybody run it
Yeah.
with 64?
Y'all have a good rest of your day.
I just did a quick Google
you as well.
search to move
No.
every second. It would be 500.
Wait, did the professor's computer turn off or something?
Yeah.
it
last
does.
second.
Yeah, he ran out of battery.
He programmed it.
He was at 1%.
He's like, show 1% when it's 2:45. I don't want to stay another second more. Act dead.
This is all still being recorded, by the way, guys.
Oh, yes.
So now everybody who watches this lecture is
I
just
mean,
gonna
it's fine. It's not like we're making fun of him.
I wonder if it's still recording.
No, absolutely
No one's
not.
gonna make it